Swayam Prabha. Digital India. Educated India.
Hello everyone, welcome back to the second lecture of our week number 6, where we are talking about different methods of stress and strain measurement. In fact, we are not talking about too many different methods here. We are focusing mostly on the resistive strain gauges, and I shall be trying to touch upon one more device towards the end of today's lecture. But we have restricted ourselves mostly to the discussion of resistive strain gauges, because that is so prevalent in the industrial measurement of stress and strain that we hardly have to think about any other option. The principle of strain gauge was introduced in the previous week itself when we talked about the measurement of length scales. However, because strain itself is something can be related to the length. Still, here in this week we have discussed about several different aspects of the strain gauges. Like in the previous lecture, we have discussed about the material for the grid and also the backing materials, different desirable characteristics of those materials, and also we have talked exclusively about corresponding circuitry. Like we have talked about the ballast circuit, which is similar to the potentiometer, and also we have talked about the bridge circuit, and we have roughly compared between both of them also. Like in case of both of them, like in both ballast and bridge circuits, for the change in or for a given amount of strain, the corresponding change in the output voltage more or less remains the same. However, in case of ballast circuit, we always have some kind of output voltage, and when you compare the strain corresponding to that corresponding to the already existing output, the change in the output voltage may be extremely small. However, in case of a bridge circuit, the normal output is always 0, and therefore, whatever change may happen, we can directly distinguish that, provided our voltage measuring instrument has sufficient resolution. Now, there are three different kinds of circuits which are commonly used along with the strain gauges. We have already discussed about two of them. The third one I was not able to discuss because of the paucity of time. I shall briefly be discussing that one today, and then moving on to discussion a few relevant parameters like the temperature compensation and also the effect of gauge orientations, etc. But before that, let us do one small exercise. So, this is not related to strain gauges, this is just related to the definition of stress and strain. So, just read the question carefully. Here we are talking about a cylindrical pressure vessel. The magnitude of the hoop and longitudinal strains on the outer surface of that cylindrical pressure vessels are given for 25 and 115 micrometer per meter length. So, if we write, then so the strains are given. So, epsilon h, which is the hoop strain, here is given as 425 micrometer per meter. Sometimes it is just also written as 425 mu, just to indicate that this we are talking about a micron change compared to some micron level change in each meter length. And similarly, in the longitudinal direction, epsilon L is given as 115 micron per meter. So, the modulus of elasticity is given the corresponding material, which is given as 103 GPa, that is we can write this as 103 into 10 to the power 9 Pascal, and the Poisson's ratio is given as 0.28. So, we have to find the value of stresses in both directions. So, we can straight away use the relation of stress and strain, which we have derived in previous lecture. If we go by that way, then how we can write, say the stress in the hoop stress in the h direction, what will be the relation for this? If you remember carefully what we derived in the previous lecture, then we can directly make use of the relation, otherwise you can derive this one. It will be E by 1 minus nu square into what? Into epsilon h will come directly plus nu into epsilon L, that is what. Similarly, the stress in the longitudinal direction will be E by 1 minus nu square into here epsilon L will come directly, and it will be epsilon H, because what is the definition of nu? It is the ratio of just these two strains only. So, in terms of nu, they are related to each other, and we have already derived these relations in the previous lecture. So, if we now put the magnitude for this one, our E is given as 103 into 10 to the power 9 divided by 1 minus 0.28 square into what is epsilon H, that is 425 into 10 to the power minus 6 plus 0.28 into 115 into 10 to the power minus 6. So, if we continue the calculation, you can just calculate the values. I have pre-calculated the numbers. So, it is coming 51.1 into 10 to the power 6 Pascal, that is we can also write this as 51.1 megapascal. Similarly, if we put the values for the longitudinal one, then you will shall be having 103 into 10 to the power 9 divided by 1 minus 0.28 square into epsilon L we have, that is 115 plus 0.28 into epsilon H, which is 425 into 10 to the power minus 6. So, if you calculate the value, again I have the number as 26.1 megapascal. So, this way, just using the stress strain relationship and using the knowledge of Poisson's ratio and the Young's modulus, we can calculate stresses in both directions. This is something that we shall be using very shortly regarding the stress measurement, because in the strain gauge we are talking about the measurement of strain, and once we know the strain, then just from the knowledge of these two parameters we can easily calculate the corresponding stresses as well. This is principally the way we go for the measurement of stress. Let us see one more parameter problem which involves resistance strain gauges now. Here we are talking about a strain gauge which is having a gauge resistance of 120 ohm and a gauge factor of 2. We are placing this one in a bridge circuit. In this bridge circuit, all resistances are also of the same value, that is 120 ohm. The power voltage is 4 volt. So, the excitation voltage is 4 volt in this case, and we have to calculate the voltage indication, means when the bridge is balanced, initially all resistances are of equal value, and therefore, the output voltage should be equal to 0, but whenever there is some kind of strain that the strain gauge is able to sense, its resistance will change, correspondingly there will be some kind of voltage indication. So, we have to calculate the voltage indication corresponding to this much of strain when we are using a high impedance detector. Means here the high impedance detector term refers that we are using some kind of voltage measuring instrument whose impedance is extremely high, almost infinitely high when we compare that with the resistance of the strain gauges, so that it does not impose any kind of loading effect. That means we are talking about this R divided by R for the voltage measuring instrument, this virtually to be equal to 0, therefore, no loading effect. This is being imposed by this particular term, high impedance detector. So, what are the given information? Here for the gauge we have R equal to 120 ohm and the gauge factor is 2. For the bridge circuit, all the resistances are of the same value, that is, if we call this one as, say, if we call this gauge resistance as R1, let us draw one bridge circuit first. So, let us say this is the bridge circuit that we are dealing with. And here this is the excitation voltage. So, this is your excitation voltage, and say one is the strain gauge and others are 2, 3 and 4. Here R1 refers to the gauge resistance, and as for the given situation R2, R3 and R4 all are equal to 120 ohm, which is the gauge resistance itself, and this EI is given as 4 volt, and we are looking to sense a strain of 1 into 10 to the power minus 6. This is the magnitude, that is 1 micrometer per meter or 10 to the power minus 6 meter per meter. This is how we are going to sense it. Though strain is a non-dimensional parameter because it is just a ratio of two length, the change in length divided by original length, but just to indicate that quite often we put this kind of unit. Now, how to do it? For a bridge circuit, we have already done the mathematical derivation in the previous lecture, I hope you remember, and what we got there? There, through our derivation, we finally ended up somewhere here, is not it? It was R1 by R1 by 4 plus 2 into delta R1 by R1, and as per the definition of the gauge factor, epsilon g is delta R1 by R1 divided by epsilon. So, if we replace this one, then we have Sg epsilon in the numerator divided by 4 plus 2 into again Sg epsilon, which means dE naught is equal to Sg epsilon into Ei divided by 4 plus 2 into Sg epsilon. So, if we put the numbers, our gauge factor is 2, epsilon is given as 10 to the power minus 6 and Ei is equal to 4 volt, that is in SI unit only. So, no need to convert. In the denominator 4 plus 2 into gauge factor is 2, resistance is 10 to the power minus 6. So, if we carry on in the calculation, we have so 8 into 10 to the power minus 6, and in the denominator we have 4 plus 4 into 10 to the power minus 6, an extremely small number. So, if we calculate this one, then we are again, I have pre-calculated this. So, we are going to get roughly 2 into 10 to the power minus 6 volt, or we can write this one to be equal to 2 microvolt. So, this is the final answer that we are looking for, that is this 1 micron amount of strain will be indicated by 2 microvolt. So, your voltage indicator should have this much of resolution, so that it is able to sense a change of 2 microvolt amount, so that we can able to sense 10 to the minus 6 level of strain or 1 micrometer per meter amount of strength. So, this is the way we can solve any problem associated with the bridge circuit or even ballast circuits also in conjunction with this resistive strain gauges. Now, let us move forward to the third kind of electrical circuit that we quite often use in conjunction with the strain gauges. It is the simple constant current strain gauge circuit. So, what we have here? Here we have a constant current source which is connected to some kind of voltage measuring instrument, which can be an oscilloscope. So, this is a, if we write properly, then this is called the constant current source. So, that is able to supply constant amount of current, and this is a voltage indicator. Now, so this oscilloscope is going to indicate the voltage, what we are going to get at the output. So, this oscilloscope is going to indicate the voltage that we have in the output, but where is the strain gauge? The gauge is mounted in parallel to this constant current source. This is the gauge of resistance R. So, if this oscilloscope is having near infinite impedance, then no voltage drop will be or no current will be flowing through the oscilloscope, rather we shall be having a current flowing only through this particular circuit. So, this current is say I. If this current is I, then the voltage that we are that gets induced across this resistance, say this voltage is E naught. Then how much is your E naught? Your E naught is equal to I into R. Similarly, if there is a change in this resistance by dR amount, then corresponding change also will be equal to this much. So, if we take the ratio of this two, dE naught upon E naught should be equal to dR by R, that is the change in the resistance can directly be related to the change in the voltage that has been sensed by the oscilloscope. And now, if we relate this one to our gauge factor, we know our gauge factor can be written as nearby R by epsilon, which gives epsilon is equal to dr by r into 1 upon Sg or divided by the strain gauge, the gauge factor. So, this way we can again use this constant current sources to measure the resistance, and if we relate this one to the voltage output, E divided by 1 by Sg. So, by measuring this particular factor using this oscilloscope or any other voltage measuring instrument, we can get the value of this strain. So, this is the third way of strain gauge circuit, though the bridge circuit is the most common one, but there may be several other situations where we are not able to use a bridge circuit. We have to go for either a ballast circuit or maybe a constant current kind of circuit. Here just one final thing before I move on to another topic, one final thing I would like to mention about the bridge circuit. We know that commonly in bridge circuit, where we have 4 resistances like this, and in the quarter bridge configuration only one of these resistances are the strain gauge, like this one. Say we generally keep this part open and this part is connected to the strain gauge, so which may be mounted somewhere here. Now, the length of these wires, they are very important. If these lengths are quite long, quite large, the magnitude of the length of these wires are quite large, then there can be significant amount of ohmic losses, or because of Joule heating losses as the current passes through these wires. So, that can also affect the final value that we are going to get in this position. So, this kind of error that needs to be avoided. These are often referred to as the lead wire errors. However, we can avoid them by using wires of very low resistances, or the more logical situation, we always have to try to keep the length of these wires short, so that the corresponding losses are minimum. Now, we move on to the next topic, which is the temperature compensation. Now, we always know that the temperature of any kind of resistance is strongly affected, or I should say the value of the resistance of any resistor is strongly affected by the temperature. Generally, the nominal value that are specified with the resistor corresponds to any particular reference temperature, and whenever the temperature varies from that position, there is a change in the resistance. So, accordingly the performance of the strain gauges are also going to get affected. There are primarily 2 different mechanisms by which we can eliminate that kind of effect because of the variation in temperature. The first one is the adjacent arm compensating gauge. This is something that we have already discussed in conjunction with the resistive strain gauges or bridge circuits. Here instead of one, we use another second strain gauge which is identical to the active one. Like here we have one active gauge which is mounted on the specimen where you want to measure the strain, but you also have another dummy gauge which is very much identical to the active one. However, it is not in contact with the specimen itself, rather it is isolated from the specimen, but still kept at a position which is very close to the specimen, so that its surrounding temperature remains also very similar to what the active gauge itself is sensing. Then what will happen? This dummy gauge, that is in this case this is the dummy gauge and this is the active gauge. Now, the dummy gauge is sensing some stress, but that is only because of the temperature, whereas the active gauge is sensing stress because of the presence of both of them, that is because of the mechanical stress plus the thermal stress. Accordingly, we can eliminate the thermal stress by comparing these two. That is what we are trying to say is that when the strain gauge this active gauge, whatever stress it is sensing, say one is coming from the mechanical part, the physical strain which we want to measure, and other is coming from the thermal part because of the temperature variation, but this one is sensing only the thermal part. So, by proper positioning or proper connection of these two gauges, it is very much possible that the net strain sensed by this particular arm is this minus epsilon t, giving or leaving out only the mechanical component. So, that depends upon the orientation of these two gauges, which we shall be discussing shortly. This is one way of temperature compensation. However, if it is there are several situations when it may not be possible to place this dummy gauge at an environment having same temperature. Like if your strain gauge is mounted on a specimen which is go through some kind of welding process, or maybe some kind of some kind of hot metal treatment, then it may be exposed to very high temperatures, and it is not possible to put the dummy gauge in any other situation which can sense similar level of temperatures. There may be several other situations also where it is not at all possible to go for a bridge circuit. We have to go for a ballast circuit. In those kind of situation, this adjacent arm compensating gauge option is invalid, and we have to depend on the second option, which is called the self temperature compensation. Self temperature compensation refers to an inherent property of the gauge itself. By proper manipulation of the alloy which we are using to make the grid, and also the proper processing of that one, we can have some control over the temperature sensitivity of the grid material. Here like what we are trying to mean is that as the temperature senses, there will be two different effects that will be coming on the gauge. One is the change in the value of the resistance because of the temperature. Second is the mechanical deformation of the gauge material and also its backing material because of the change in temperature. Like if the temperature increases, there will be an elongation of the physical length of the resistance and also its backing material. So, if we can treat the alloy properly and process and fabricate the gauge properly, then it is possible that these two opposing factors may eliminate each other over a over some range of temperatures. Like the figure that is shown for a situation, there you can see over this particular range, the value, the corresponding apparent strain is extremely small. In fact, we can extend this one to a level somewhat like this also. Means over this range of 10 to 50 degrees Celsius, we can say that we do not need any other kind of compensation. The device itself is able to go for some kind of self temperature compensation, and thereby corresponding temperature induced apparent strain remains extremely small within this range only. However, if the temperature range that we are dealing with, that is quite large, this one may not be able to sustain, but we can by proper metalworking we can develop gauges which can maintain a near constant value of the gauge factor over a sufficiently long range of long interval of temperatures. So, long means I can say it can be in the range of 200 to 300 degrees Celsius, and also we can develop gauges which shows this particular property in different ranges of temperatures. Therefore, depending on which range of temperature we are dealing with, we can choose the corresponding gauge, and we hardly have to think about any kind of temperature compensation then. The similar effect can also be obtained if we use two different grid materials having different temperature characteristics and connected in series in a single gauge. But here importantly we have to control the temperature characteristics of both materials properly, and we have to connect them suitably as well. Then the combined effect of these two gauges will also be more or less independent of the temperature effect. But still temperature compensation is a very important tool that we always have to be mindful of whenever working with the resistive strain gauges. Next, we discuss very briefly about the stress strain relationship. One option can be simple uniaxial stress situation, where we know that the stress and strain remains linearly proportional within the elastic limit, and so once we know the value of this E, then just the knowledge of epsilon gives you the value of this corresponding stress. Like the values for the epsilon or the order is shown for different kind of material, whereas material like rubber can have only in this range, still they have much higher level, much higher modulus of elasticity, and so the knowledge of this E therefore can very easily give you the value of corresponding stress only from the strain measurement. However, this is when you are talking about uniaxial stress, that is a force is applied only in one direction. But practical cases we may have to go for biaxial stress measurement, where the stress is acting in both direction, and there along with the modulus of elasticity you also need to know the value of this Poisson's ratio. And how we are going to use it? Just like the problem that we have solved today to start with, like the stress which is acting in a particular direction, say sigma x, we can always write this as E upon 1 minus nu square into epsilon x plus nu into epsilon y plus epsilon z. So, all three strains are contributing for the final calculation of epsilon x. Similarly, we can calculate, say the epsilon z is our interest, then this will become 1 minus nu square into epsilon z, which is the primary direction, plus the Poisson's ratio into the other two, or summation of the other two. So, this way we can calculate the biaxial stresses. If the principal direction is not known, then however it is not possible to identify the maximum stresses. Like x, y, z, these coordinates are only theoretical idea, and a practical stress measurement situation, you may not be completely knowing the corresponding coordinate directions or the direction of application of the forces, or the application of force, the direction of force may keep on changing during a dynamic measurement scenario. So, in that case we can't just use one gauge and get the idea about all three different kinds of all three components of the stresses, or rather we just can't place the gauges which can directly give you the value of this epsilon x, y and z. Rather we have to go for some kind of combination of strain gauges, and then we have to calculate the maximum and minimum value of the corresponding strains by suitable mathematical manipulation. At least 3 such strain gauges are required to obtain any kind of combination when operating with unknown principal directions. But sometimes a fourth gauge is also incorporated, which can act as a check for the correctness, and such kind of combination of gauges are known as rosettes or gauge rosettes. Rosettes primarily primary is a combination of 3 different parameters like shown here. This is just one particular rosette, which is very commonly called the rectangular rosette. Now, in this particular rosette you can see there are 3 gauges and they are placed 90° apart from each other. So, each of them, say this one A, this is B and this is gauge number C. So, each of them is showing a reading of corresponding strain in that particular direction. Now, we have to combine them to identify the maximum or minimum strain that is acting in this situation. Let us assume that the maximum or minimum strain is acting in some theta direction. We have to identify the magnitude of this particular thing and also the magnitude of the theta. So, I am not going for the mathematical calculation, that can be obtained quite straightforward way, but what we can write is the final result, where epsilon 1 and epsilon 2, which can refer to maximum and minimum stresses. It is not that the epsilon 1 is always larger, epsilon 2 may also be larger, but these two are the two extreme values of the stresses. So, if we do the calculation properly, their values will be something like this: epsilon A plus epsilon C plus root, or rather I should say, again the problem with writing in the pen. So, plus minus root of 2 into epsilon b minus epsilon a whole square plus 2 into epsilon b minus epsilon c whole square. So, once we know the value of epsilon a, b and c, then we can always combine these three to get, when we are using this plus we are talking about the maxima, when we are using the minus we are talking about the minima. And what will be the corresponding principal stresses? Say if sigma 1 and sigma 2 refers to the two direction of the principal stresses, then that will be equal to E by 2 into epsilon a plus epsilon c. Here I have written epsilon 2 in the previous case, that should have been epsilon c. Epsilon c by 1 minus nu, no, it should have been minus 1 minus nu plus minus 1 by 1 plus nu into, within square bracket the same term, that is 2 into epsilon b minus epsilon c whole square plus 2 into epsilon b minus epsilon a whole square. So, this allows us to calculate the value of the strains in the corresponding epsilon 1 and 2 directions, the two principal directions. And how can we identify the value of this theta? The same way we can calculate the value of this tan of twice of this theta, generally is given as twice of epsilon b minus epsilon a plus epsilon c divided by epsilon a minus epsilon c, which will give you the value of theta. Generally you can get two different values of theta working in two different coordinate directions or in two different quadrants. Now if the value of this twice of epsilon b is greater than epsilon a plus epsilon c, then we can say that the theta lies between 0 degree and 90 degree. However, otherwise the theta lies in the other coordinate, that we are going to get by solving this particular situation. I say it is plus 90 degree, where we are talking about plus in the counterclockwise direction like shown here. Let us deal with a small problem here. We are not deriving these equations because these are quite standard equations, we hardly have to remember them also. But here we are dealing with a situation where the material properties are given as modulus of elasticity is 207 GPa and 0.3 as the 0.3 as the Poisson's ratio, and the values of the strains in three directions A, B and C are shown here. So how can we calculate the values? Let us first calculate their square root. So the value of the square root, that is 2 into let me start writing from top so that we can get some more space. So 2 into epsilon b minus epsilon c whole square plus 2 into epsilon b minus epsilon a whole square, that is if we put the values, 2 into epsilon b is 120 minus 72 whole square plus 2 into 120 minus 248 whole square, and the calculation of this one is giving us 193 mu or 193 micron per meter. So how we can calculate? Now epsilon max then will be equal to half into epsilon a, that is 72, plus epsilon c, that is 248, plus the particular one that we have just calculated, that is 193. So if we put the numbers, it will be coming 256 micron or micrometer per meter. Similarly, epsilon min will be equal to half into 72 plus 248 minus 193. So the value is going to be coming to be 63 micrometer per meter. And if we want to calculate the stresses, so sigma max will be equal to, we can put the numbers here, the modulus of elasticity is given as 207 into 10 to the power 9 divided by 2 into epsilon a plus epsilon c. So epsilon a is 72 plus epsilon c is 248 divided by 1 minus 0.3 plus minus, or sorry, we have to put the plus sign here as we are trying to get the maximum here. So 1 by 1 plus 0.3 into the square rooted value which we have already calculated here, which is 193 into 10 to the power minus 6 we are taking out, because remember this 72, 242 and 193 all are having 10 to the power minus 6 incorporated. In fact, in this calculations we have should have also written 10 to the power minus 6, because here all the values are given as micrometer per meter. So this is epsilon max, and if we put the number, you are going to get 62.68 MPa. Similarly, sigma mean, how much it will be? Here this positive sign will become negative, or because here we have this plus minus sign. So once we put the minus sign, then you will be getting this one as 31.94 MPa. I am just giving you the final numbers, you can calculate and get the final values of whatever you have. So now we have to get the direction, in which direction this epsilon max and mean are working, or the principal direction for this. So tan 2 theta is equal to twice of epsilon b, that is 120, minus epsilon a is 72 plus epsilon c is 248 divided by epsilon a minus epsilon c, that is 72 minus 248. So, if you put the values here, then 2 theta will be coming to be 25 degree or 205 degree approximately, which gives theta equal to 12.5 degree or that is 102.5 degrees. Now, which one will be the correct answer? That will be coming from this criteria. Let us check the value of epsilon a plus epsilon c. So, epsilon a plus epsilon c in this case is 72 plus 248, that is 320, and twice of epsilon b is 2 into 120, that is 240, or I should write 240 mu and 320 mu. Now, this one is greater in this case. So, what does that indicate? Theta, had this twice of epsilon b greater than this quantity, then it would have lied in the first quadrant, but as this is smaller, so it is not lying in the first quadrant, then your value of theta is 102.5 degree. This direction on which the maximum or minimum stress is working. This way you can do the calculation for any strain gauge rosettes. There are several other strain gauge rosettes also. This is the most standard one, the rectangular strain gauge rosette, but another one I would like to talk about, and that is a delta rosette, or also called the equitriangular rosette, because instead of presenting this way, we could have also presented this as 3 triangles like this, where say A, B and C are the 3 strain gauges. Again here I am directly writing you the expressions epsilon 1 and epsilon 2. If we do the calculations properly, then you are going to get as epsilon A plus epsilon B plus epsilon C plus minus, and this plus minus will decide whether you are talking about the maxima or minima, plus for maxima, minus for minima. So, again we have a root 2 into epsilon A minus epsilon B whole square plus 2 into epsilon B minus epsilon C whole square plus 2 into epsilon C minus epsilon A whole square. So, this is a quite straightforward formula, we can easily calculate this, and similarly if you put say sigma 1 and sigma 2, then that will be equal to, just definitely E will be coming in E by 3, rest part remains quite same. Like if we compare the previous case, whatever we had before the square bracket, that was divided by 1 minus nu, here also it is being divided by 1 minus nu, plus minus what we are going to have 1 by 1 plus nu, and this entire square term, the same square term or square rooted term that we have in the previous line. And the criteria for tan theta in this particular case, or tan 2 theta, it is slightly different. It is root 3 into epsilon c minus epsilon a divided by twice of epsilon b minus epsilon a minus epsilon c, and the criteria is if epsilon c is greater than epsilon a, then theta will lie in the first quadrant. So, using this we can calculate the calculation for this delta rosette. So, we have talked about the triangular and the equitriangular, or you can or I should say the rectangular and the equitriangular, or commonly called the delta rosettes, and some rough mathematical relations that are given about. So, once we know the values of all these 3 resistances, that is A, B and C, or epsilon A, epsilon B and epsilon C, we can easily calculate the maximum and minimum stresses and also the direction of principal stress. Thereby we can combine 3 resistances. These are just 2 examples, but we can combine resistances in different other combinations, or I should say resistive strain gauges in different other orientations, just to get an idea about the maxima and minima, about the minimum strain gauges, maximum stress that is acting on the system and the direction of its application. There is another variation of this delta rosette that is quite often is also used, where we have the same 3 resistive strain gauges A, B and C. However, there is a fourth one which is also put in from the center point of this A, that is D, and this D is used, like we have mentioned earlier, D is generally used to check the correctness of the solution or correctness of the measurement for this. This particular one is called a delta star orientation, or sometimes also called more popularly a T delta orientation, because the bottom part looks like an inverted T, that is why it is often called a T delta orientation. These are just three common examples of strain gauge rosettes, but we can have several other orientations also, which may be very difficult to deal with, at least through simple analytical cases, such situation. Finally, we have to talk a bit about the orientation of the gauges. When we are talking about a bridge circuit, we like in a quarter gauge configuration, we connect the strain gauge with one of the arms, that is, one of the resistance in the bridge is being replaced by the strain gauge. However, if we are going for a half gauge, we replace two of the resistances, and in a full bridge configuration, all the 4 resistive strain gauges or all the 4 resistances of the bridge are replaced by corresponding strain gauges. Now, which of the configuration we should go for, or if we are combining 2 or 3 or 4 strain gauges into the same configuration, how we can calculate the final value, that we would like to check very briefly here through some kind of mathematical orientation. So, let us consider first a bridge circuit. So, this is the standard Wheatstone bridge kind of circuit that we have. Let us say this is resistance 1, this is 2, this is 3 and this is 4. Let us give some names, say this point is A, this B, this is C and this is D. Here we have the source. So, our source is some DC source having a voltage of EI, and our final measurement is taken across these 2 points between B and D. So, EO is the measurement voltage. So, when 1, 2, 3 and 4 all resistances have their nominal values, then E0 should ideally be 0. This one will show a 0 voltage value. However, whenever there is a deflection in any one of the arms, or maybe at least in one of the arms, we are going to get some value of this. Let us first try to relate this E naught with the resistances with an exercise which we have already done in the previous class for such bridge circuits. So, what will be your E out? That definitely is EB minus ED. Now, how much is your EB? We can make use of the current that is flowing through this circuit, and from there we can say that EB should be equal to EI into R2 divided by R1 plus R2, the resistance of that particular side, and ED should be equal to EI into R4 divided by R3 plus R4. That is, if we simplify this, then we have R1 plus R2 into R3 plus R4 in the denominator, and in the numerator what we have? We have R2 R3 plus R2 R4, which cancels out, minus R1 R4. So, this is what we are having in the numerator. Now, let us assume that 1, 2, 3 and 4 all can act as strain gauges. That is, in a situation all of them can change, or maybe any one of them can change, or any of any of the resistances can change their values. That is, R1, R2, R3 or R4, any one of them or several of them can change simultaneously, thereby causing a change in this E naught. So, correspondingly d E naught can be calculated as not dou R1 into delta R1, or just to be consistent with the notation, should write as say d R1 plus R2 d R2 plus dou R3 d R3 d R4. So, make use of the previous line, EI being a constant, I am taking it on the left hand side. So, if we make use of the previous line, what is going to be what is going to be the differentiation? First we have to differentiate this expression with respect to R1. So, if you differentiate with respect to R1, then what we are going to get? We are if we differentiate with respect to R1, say let us calculate the first part, dE naught dR1. So, what we have? We have EI as outside, in the denominator R1 plus R2 whole square, R3 plus R4 it is a constant. So, that whole square, the whole square. In the numerator, differentiating with respect to R1, each resistance are independent of each other. So, we are having minus of R1 plus R2 into R3 plus R4, the entire denominator. And now what we are having here, R2 R3 R1 R4, that is the numerator, into the differentiated form of the denominator with respect to R1, which is just R3 plus R4. So, R3 R4 one cancels out from there, that is EI. So, what we are left with is minus R1 plus R2 minus R2 R3 plus R1 R4. So, R2 R3 R1 R4 divided by R1 plus R2 whole square by R3 plus R4. Have I missed something? I feel I have missed something when doing the first step. Numerator, in the numerator, okay, there should have been an R4 in the numerator, which I have missed. So, it is minus R4 in the numerator, that means we have an R4 here. This. So, if we simplify this, that is minus R1 R4 cancels out. So, we have EI into, in the numerator, R1 plus minus R1 R4 cancels out, and we have minus of R2 R4 plus R2 R3, because R1 R4 cancels out by R1 plus R2 whole square, R2 plus R3. And if we simplify it even further, taking R3 plus R4 common, this is R3 plus R4. So, if we simplify it even further, then it becomes, if we take R3 and R2 common from the numerator, we have just R2 left in this EI by R1 plus R2 whole square. So, this is what we have. So, if we take it back there, so this will become minus R2 by R1 plus R2 whole square, plus the same way we can continue with the others. So, it becomes minus R1 by R1 plus R2 whole square dR1, this is dR2, minus R4 dR3 by R3 plus R4 whole square plus R3 dR4 by R3 plus R4 whole square. This is the entire expression that we are dealing with now, and I just want to ensure if I have made any mistake with the symbols anywhere, because that will lead to a wrong expression at the end when you are differentiating this first with respect to R1. So, this is what we have now. Let me erase this entire portion to make some more space for the next part of our calculation, and this plus sign then will also become negative in that case. Now, in a special situation, actually not a special, in most of the common gauges you will find this R1 R2 all are equal in magnitude, means all of them are, all the resistances in the bridge are given the same value. equal to R. In that case, what we have, d E naught by E I, putting the values as R. So, we have minus of 1 by 4 R into d R 1 plus d R 2 plus d R 3 plus d R 4, and if we replace this, now we know that, say for the first gauge, say Sg will be d R 1 by R divided by epsilon 1. So, if all of them generally are having same gauge factor, then we can always replace this one as minus 1 by 4 into Sg into epsilon 1 plus Sg into epsilon 2 plus Sg. So, I should write this as Sg for the gauge 1, this is Sg for 2, Sg for 3 epsilon 3 plus Sg for 4 epsilon 4, and if all gauge factors are equal, then this will become minus Sg by 4 into epsilon 1 plus epsilon 2 plus epsilon 3 plus epsilon 4. So, depending upon what is our objective, we have to connect the gauges properly. This gives us a way of connecting multiple gauges, whatever may be the orientation that we prefer. Like if we are talking about only a quarter bridge, say where the strain gauge is connected only in the arm 1, then epsilon 2, 3, 4 does not have any value, because they are all 0, because they are fixed resistances. However, epsilon 1 will be there. Whereas, if suppose 2 and 4 are the arms where you have strain gauge connected, then only epsilon 2 and epsilon 4 will be there in the picture. This way, we can combine several strain gauges to obtain a proper circuitry of gauges, and we can most commonly go for this bridge orientation to get the final reading. So, this is all for resistive strain gauges, which is the primary instrument for measurement of strain and stress. However, I briefly would like to talk about another kind of gauge, which is the variable inductance strain gauges. Similar to the displacement measurement, like resistive instrument, we can also have inductance and capacitance based instrument, and that is why this is a very brief introduction about the variable inductance strain gauge. Here we have a moving iron armature, and the instrument for which we want to measure the strain of the specimen, that is connected with this armature. So, in the initial position, the armature is at the neutral position between coil 1 and coil 2, so that the voltage induced in the both the coils are equal. Now, if there is any strain because of which the armature moves closer to the left core, that is closer to this particular one, then the inductance in coil 1 will increase and inductance in coil 2 that will decrease. So, correspondingly, the impedance produced in the corresponding Z circuit, Z1 corresponding to coil 1 and Z2 corresponding to Z2, they will not remain same, and an output voltage E will be produced, which should be proportional to the displacement of this moving iron armature. Similarly, when the coil moves towards right, that is towards core 2, then the inductance in core 2 will be higher compared to the core 1, and so the Z1 and Z2 values again will change. Accordingly, it will produce again a voltage E. If the movement is same, movement towards right and movement towards left are same, then the magnitude of E will be same, but its symbol will be different. That is the way we can get a quite accurate measurement of the strain and also the direction of the same as well. However, this instrument generally is quite bulky and complex in construction, then therefore, they are mostly used either in a permanent installation or more commonly both inductance and also similar sort of capacitive based strain gauge. They are used more for measurement of secondary parameter, that is, instead of strain we are measuring strain, but our final objective is not to measure strain, rather something like say pressure or flow. In those kind of situation, generally we go for inductance and capacitance based instruments. So, if such situation appears when we talk about those parameters, we may be discussing a bit more about inductance or other kind of strain gauges, but just to finish on, I would repeat again that the resistive strain gauges are the most common type of measurement tool that we use for practical measurement of stress and strain, and that is why this entire lecture and also the previous one, that is this entire module, we have discussed only about the resistive strain gauges and different aspects of the same. So, that takes us towards the end of this particular week. We have kept it quite short because if the idea of strain gauges are already discussed in the previous week, and here we have just tried to see some of the practical aspects like the material, like electrical circuitry, and like the combination of different gauges either in the bridge circuit or in the form of rosettes. That is what we have tried to see. So, what we have learned, just a very brief summary. We have talked about the stress strain relationship to start with, then we moved to the resistive strain gauges. First we discussed about the materials like I just mentioned, then electrical circuitry we have seen that there are three kinds of circuits which are commonly used in conjunction with the strain gauges. The ballast circuit, which is similar to potentiometer, the bridge circuit, very popular, and some situations we can also go for a constant current source based circuitry. Then we have discussed about the option for temperature compensation. When we are using a bridge circuit, we generally go for the adjacent arm based compensation. However, if the arm it is not possible to put a bridge circuit, or if it is not possible to have multiple strain gauges or a dummy strain gauge located in proper environment, then we have to go for, or we have to depend on the self temperature compensation, which can be achieved by proper material working. We have discussed about the strain gauge rosettes. Primarily we have discussed about the rectangular and equilateral or the delta rosettes, and effect of gauge orientation was briefly touched upon, and finally a very brief introduction about the variable inductance strain gauge. So, that is it for module number 6. Please go through the lecture, try to study the books and solve the assignments. If you have any query, please write back to me, I shall be very happy to answer. And several mathematical derivations that we have done in this particular module and also in the previous week. If you have any difficulty, I would suggest that first you try to do that on your own without listening to the lectures or without looking into the books, and if you find any difficulty, then first look at the books. Otherwise, please write back to me, I will try to again clarify. So, that is it for this week. I am signing off from here, and we shall be seeing again in the next week, where we shall be talking about the measurement of force and torque. So, thank you very much.